We are going to look at the assumption of the classical linear regression model. And when we look at the classical linear regression model, there are some assumptions the model has to meet. If your model fails to meet any of these assumptions, then the estimate from such model will be biased. And to use such kind of biased model to make a prediction, or to use such kind of biased model in policy purpose, will actually lead to error in policy making. So we are going to look at some of these assumptions in a classical linear regression model. We are going to look at 4 of those basic assumptions. We are going to ignore the other ones. But once any of this assumption is violated, then your model, there is a bias in the estimate of your model. Such model it will lead to wrong policy formation, or will lead to wrong decision. So among this, we are going to look at the case of multicollinearity. We are going to look at the case of homoscedasticity. We are going to look at the case of autocorrelation, and we are going to look at the normality assumption, whereby the stochastic error term are expected to be normally distributed. Now we talked about the multicollinearity. Now to look the word multi and word collinearity. Now the linearity talks about once there is a linearity, a linear relationship among an independent variable. In other words, if the independent variable influences each other and this now have effects on the dependent variable, then that means that particular model, if estimated, is biased, and such kind of model cannot be used for decision making, or can we use it for policy formation. For instance, we are looking at the influence of quantity, on the influence of price on quantity demanded. Now we have a lot of factors that affect the quantity demanded of a particular product. Now, if we decide to look at substitute or complementary goods, we're looking at the price of substitute good and or the price of complementary goods. And we are now looking at the price of the good itself. Now, the price of the goods itself can also influence the price of substitute commodity. Now, if both variables are included in the model, such can lead to a problem of multicollinearity, because once the price of the particular commodity in question increases, it can also lead to increase in the price of the substitute of that commodity, of the substitute of such commodity, which will also lead to a decrease in the quantity demanded of that particular commodity. Therefore, when I run into estimating such model, one can run into the problem of multicollinearity. Now, it's multi in the sense that we are looking at more than one variable. Now look at the problem of homoscedasticity. Now, the problem of homoscedasticity, now we are looking at it is assumed that your random error term for your model is constant throughout the period of your analysis. That for each independent variable, the error term is constant throughout for each of the independent variables. Once this assumption is violated, then that means your data set is not normally distributed. That is, the normality assumptions is that homoscedasticity assumption has been violated. Then we talked about the problem of autocorrelation. Now, the problem of autocorrelation also has to deal with error term, that error terms is not correlated with each other. Now, for multicollinearity, we are looking at the independent variable, where our independent variables are not correlated. But when it comes to autocorrelation, we are looking at the error terms, that the error terms are not correlated. That is, a error term for a particular variable does not influence the value of the error term of another variable. Once this assumption is violated, there is bound to be a bias in our model, and such kind of model cannot be used for policy purposes. Then we have the one of the stochastic error term. The stochastic error term of our data set is expected to be normally distributed. There are other assumptions in the classical linear regression model which we are not going to look at, like talks about the linearity in parameters and the rest of them. But these four major assumptions are very, very important, that once violated, once any of these four assumptions is violated, your model, your estimate is biased, and such estimates cannot be relied upon for policy purpose, or neither can it be relied upon for decision making. Now, let's quickly go into my app. Now, I'm going to import my dataset using this. So if you have not imported your dataset into this app, make use of this code. You run this line of code. This line of code we install this particular package with Excel. Now, this particular package helps to import the dataset. Now, my dataset is in Excel spreadsheet, so this will help you to import your dataset into Excel spreadsheet. Why this will activate it? So I already have it installed in my app. Then this migrate, now because I want to use a pipe function, I have to use this because I want to use a pipe function. Now, this is the pipe function. I want to use the pipe function. So because of that, I have to install that. So now, normally this comes with your app. So, but if it's not installed in your app for whatever reason, you can quickly install that. So the next thing we are going to do, we are going to run this line of code, and my file, this is a file I want to use, car sales for, and it's located in this folder, our program. Now, this is the our program, and the our program is in documents. So I can run either this line of code or run this line of code to install to import that dataset into our. Now you can see this is my dataset. Well, when I click on that, I can see my dataset. Now I can see the manufacturer of the cars and the model of the car, the sales of the car. Now I'm interested to see the influence of the engine size of a car, the influence of the engine size of a car, the fuel efficiency of a car represented by the MPG variable on the sales of the vehicle. This is what I'm interested in looking at. Okay, now I've imported that. Now in order to check if there is a multicollinearity in among your variable of interest, now we can make use of the correlation coefficient. Now we are going to use the correlation coefficient. We are going to use the correlation coefficient. So in order to compute the correlation coefficient in R, I'm going to use the COR function in R. So now I have the COR function in R. I have to specify my X and my Y. Now, since my data set, I have more than one columns in my data set. So what I need to do is this. I will bring in my data set. I'll specify my data set, then I'm going to introduce the dollar sign in order to pick the variable of interest. So I'm interested in sales, now comma, then I'm going to bring in my data set and bring in the other variable of interest by introducing the dollar sign. Now bringing in the other variable of interest, that's my car sales, and I'm interested to see the engine size. Okay, now the other variable of interest is now the car sales, and we are even looking at our independent variables. So we really need not to bring in the sales, which is the Y. Okay, now I also want to see between the car sales and the car sales and fuel efficiency. Okay, that is MPG. Okay, then also I want to see the relationship between the fuel efficiency and the engine size of the car. So let's look at that. Now, with this, I can run individually. I run this and see the correlation coefficients of each of these variables. Now, car sales and fuel efficiency. That gives me a negative correlation. Now, take note by default, R runs the Pearson correlation coefficient. So this is how to do that in R. Now let's see how if I want to run this in SPSS. I want to run this in SPSS. So I go to the analysis menu and I go to correlation. Now I'm interested in two correlation coefficients, that's the divariate correlation coefficients. Now these are the three variables of interest here. For now, these are my three variables of interest. Now we have different types of correlation coefficient. We have the Pearson, we have the Kendall, and we have the Spearman. Now by default, our studio runs the Pearson correlation coefficient. Okay, fine. Then I could decide to use this if I want to. So I'm okay with this. All I need to do is to click on OK. Now, when I click on OK, you can see the relationship between the correlation between the sales and the engine size of the car is 0.02. Now, that is a very low correlation coefficient between the two. What did I get in R? When I did that in R, correlation between sales of car and fuel efficiency, I have approximately 0.06. Now that is similar in both cases. Then the other one I looked at, the correlation between the engine size of a car and fuel efficiency. Engine size and fuel efficiency, I have a negative correlation 0.735. 0.735. Now let's see what do we get that. Okay, let's talk about engine size of a car and what fuel efficiency. Now the engine size of this car and fuel efficiency. Now look at what I got here. I got minus 0.4875. Now you can see there is a discrepancy in that. But let's look at the sales of a car and the fuel efficiency. Sales of the car and fuel efficiency. Okay, let's see sales of a car and fuel efficiency. I got minus 0.012. Minus 0.012. Okay, that is minus 0.017. Now that is approximately minus 0.02. Now fine, but the difference here we have is fuel efficiency and the engine size of the car. So let's try to see why that difference is. Now fuel efficiency and the engine size of the car. Look at what we got here. So we have minus 0.735. Oh, that's what we got here. Minus 0.035. That is what we got here. Now look at the number of variables. I'll use 154. How many segments have been permanent on along there? Because what we have here is minus 0.0475. And then we make use of Pearson, which is by default. I'll use Pearson by default method. We could look at method. I'll make use of Pearson by default. Should we use Pearson? Let's see. Spearman, the Spearman rank correlation coefficient doesn't really really goes on with when you are working with the ties. Okay, fine. Now you can see when I make use of the Spearman, I got something closer, minus 0.738. So when we go to this, we can see we have minus 0.735. That is very, very well close to that. So that is also wrong to correlation coefficients in SPSS and also in our studio. Okay. Now when you look at the R runs the correlation coefficients all at once. But in SPSS, I have to run it one after the other. So let's see how we can do that. Now we can decide to select a variable of interest. Select the variable of the sales, the engine size, and the fuel efficiency. So in order to do this, we have to bring in the car sales, that is our dataset. Now we have to bring in the car sales, our dataset, and we introduce the pipe function. Now because of the pipe function, that is why I installed this. So ensure you have it installed in order you can make use of the pipe function. Then we introduce the select function. Now the select function, we are going to select 3 of those variables because my data set has many columns. I'm only interested in just 3 columns. So I want to select those 3 columns that I'm interested in my data set. So the other one is the engine size, and the last data set I'm interested in. The last data set I'm interested in is my MPG. Okay, that is the last data set I'm interested in. So the moment you run that line of code, okay, we run this line of code. That okay, what's the telling us? Can't convert cash sales debit into the date lost. Okay, date lost of something there. Okay, something precision or okay, class sales. Sorry, we made a mistake. Okay, now we can see now we've selected that variable. So now this data set is now only 3 variables. So we can now save this data set and call it and we are looking for we are interested to see the correlation among the variables, so we can call it we can say car sales correlation. So we can save it in that object known as car sales correlation, and we run this. When we run that line of code, you can see car sales correlation. We only have 3 variables. Well, when I open it, you can see we only have 3 variables. It has selected only the 3 columns out of all the 4 columns. So now I can now run this, and I can now run this and pass that into the correlation function. Now, once I run this, it will not give me the correlation metrics, but when the variable of interest. Now you can see it gives us the correlation metrics, which is similar to what we got using the individual correlation. So this also run correlation in R and in SPSS. If you love this video, kindly give it a thumb up, and also don't forget to subscribe to our YouTube channel, and Instagram channel, and our TikTok channel.